Okay, cool. So we have LNL section 11, problem 1. And this problem states to determine the period of oscillations of a simple pendulum, a particle of mass m suspended by a string of length L in a gravitational field, as a function of the amplitude of oscillations. So if we draw our system here, we have our x-axis, our z-axis, and a string of length L suspending the pendulum, and this string is going to be making an angle I will call phi naught with the z-axis. Now I'm going to take my potential energy equal to 0 here, so all of this is going to be negative potential, and if we use the conservation of energy, we would be able to integrate equations of motion for the system. So at our maximum, we have, as the pendulum moves up, it stops for a short period of time, and at that moment it stops, its kinetic energy is equal to 0, and its potential energy is just equal to U equals minus mgz. Now, the goal of this integration is to set it up in terms of a complete elliptic integral of the first kind, which a complete elliptic integral of the first kind is the integral from 0 to pi by 2 of d theta over the square root of 1 minus n squared sine squared theta. Now, these integrals can be used to describe anything all the way from planetary motion down to a simple pendulum, like I will show here. And if we describe our energy as the pendulum is moving, it can also be described by t plus u, and our u is also going to be equal to minus mgz. So the first thing we need to do is to figure out a way to describe the z-axis of the pendulum. This can be done by noticing that the position of the pendulum makes a right triangle with the z-axis. Thus, the z-axis would be correspondent to the cosine of the angle that is being made with phi naught. So if we describe it as E naught equals minus mg L cosine phi naught, and our E is equal to T minus mgl cosine phi. And I'm going to denote this as just phi because this is the system, or the system where the pendulum is moving. Phi naught would represent when the pendulum is at its maximum and it comes to a complete stop for a short period of time. Now all that's left is to describe the kinetic energy of the system as it's moving. And we know this from basic mechanics to be 1/2 mv squared, which our velocity vector is taking this arc length trajectory here. So we can just denote that if we write our kinetic energy as 1/2 m ds dt squared, because it's an arc length, our s in this case is just equal to L phi. So our total kinetic energy can be represented as 1/2 m L squared phi dot squared. I'm going to denote the dot as the derivative with respect to time. So from here we can simply note that the conservation of energy means that these two must be summed, or one must be equal to the other. So if we write it as such, we have minus mgl cosine phi naught is equal to 1/2 ml squared phi dot squared minus mgl cosine phi. And rearranging this, we get 1/2 ml squared phi dot squared is equal to mgl cosine phi minus cosine phi naught. And we now see some really nice cancellation happening. The m's cancel out, the L squared cancels this L and becomes a divisor, and the 2 goes in front. So we have phi dot squared is equal to 2g over L cosine phi minus cosine phi naught. Taking the square root of both sides, we would get phi dot equals square root of 2g over L cosine phi minus cosine phi naught. And from here, we can say that it is going to be equal to dt. And our pendulum, as it moves from its maximum position, if it is here, it moves to the position of least potential energy, then to the opposite of maximum potential energy. So it takes path 1, path 2, path 3, and path 4, all the way back to get to its original starting position here. So our bounds of integration would be integral from 0 to phi naught of d phi over cosine phi minus cosine phi naught, all inside of a square root. And we would get square root of L over 2g would be equal to, since it takes 4 of the time interval to reach the original position again, it would be 0 to the period over 4 dt. Thus, this sets up our integration for the equations of motion. The right-hand side is simple. We would just get t over 4. Moving the 4 to the other side, we would get 4 times the square root of L over 2g, integral from 0 to phi naught of d phi over the square root of cosine phi minus cosine phi naught would be equal to the period. And simplifying the expression in front of the integrand, it would be 2 times 2, which gives us 4 over the square root of 2. And anything over the square root of 2, or 1 over the square root of 2, is just equal to that over the square root of 2, or that times the square root of 2, my bad. So this can just be written as 2 square root of 2. So we have 2 square root of 2 integral from 0 to phi naught of d phi over cosine phi minus cosine phi naught square rooted would be equal to the period. Now, if we use the double angle formula to represent cosine phi, we have cosine phi is equal to 1 minus 2 sine squared of phi by 2, and the same can be done with phi naught. 1 minus 2 sine squared of phi naught by 2. And we write these into our expression for the integral. So we now have 1 minus 2 sine squared phi by 2 minus 1 minus 2 sine squared phi naught by 2. All of this is going to be inside of the root, and this is all going to be the divisor for d phi, and we still have our integral 0 to phi naught and 2 square root of 2 times the square root of L over G. And all of this would be equal to the period. Now we have some nice cancellation going out here, 1 minus 1. If we factor out this square root of 2 from both sides, we get square root of 2 outside, allowing us to cancel this. So our new integrand becomes 0 to phi naught of d phi over sine squared phi by 2 minus sine squared phi naught by 2. And we have 2 times the square root of L over G. All of this would be equal to the period again. And it is also all inside of a square root. So if we were to factor out a term of sine squared phi naught by 2, because we're integrating over phi, not phi naught, so phi naught is just a constant, we would get sine of phi naught by 2 times the integral of 1 minus sine squared phi by 2 over sine squared phi naught by 2. All of this as a divisor for d phi. And integral from 0 to phi naught 2 times the square root of L over G. And I'm going to go ahead and note that there so we know that that's inside of a root. All of this equal to the period. So if we let's make a clever substitution here. If we I'm actually going to go ahead and move this down as well so I can have more space to work with. If we let sine squared of phi by 2 over sine, not squared, sorry, just sine of phi naught by 2 equal sine theta, then 1/2 cosine phi by 2 d phi equals sine phi naught by 2 cosine theta d theta. And solving for d phi, we get that d phi is equal to 2 sine phi naught by 2 cosine theta d theta divided by cosine of phi by 2. And if we make the same substitution that we made before, where cosine phi naught by 2 actually we'll be using a different one this time, is equal to 1 minus sine squared phi by 2, all inside of a square root, because 1 minus sine squared theta is cosine squared theta. And we replace that into our term. We can also write that this term, sine squared phi by 2, we have that term here, just not squared. But it's also inside of a square root, so we can also just write it as sine phi by 2 is equal to sine theta sine phi naught by 2. So our final term for d phi now becomes 2 sine phi naught by 2 cosine theta d theta over sine theta sine phi naught by 2, 1 minus that, all inside of a square root. So we can now write our integrand in terms of theta instead of in terms of phi. So we have 2 times this 2 right here that we get from d phi. So we now have 4 times the square root of L over G times the integral. Now our bounds, when phi equals 0, my bad, phi would be equal to 0, and we let this term all equal to 0, sine theta would also be 0, and when it equals phi naught, this term becomes 1, so sine of theta has to be 1, thus it equals pi by 2. And from there, we can write our term for d phi, which would be sine of phi naught by 2 cosine theta d theta over the square root of 1 minus sine phi naught by 2 sine theta inside of a square root. And from previously, we also had one minus sine squared phi by 2 over sine squared phi naught by 2. All of this also inside of a square root. Now we notice that this term here is just equal to sine theta. So this would be equal to 1 minus sine squared theta, all inside of a root. And we also had this term here, sine phi naught over 2. All of this would be the new transformation from phi to theta. And from here we can see some very nice cancellation happening. Sine phi naught by 2 cancels with sine phi naught by 2. 1 minus sine squared theta is cosine squared theta inside of a square root. That becomes just cosine theta. Thus our integral now becomes 4 times the square root of L over G, integral from 0 to pi by 2 of d theta divided by 1 minus, and if I call n equal to sine squared phi naught by 2, then I was also supposed to have a square here from the cosine portion of it. So n is equal to sine phi naught by 2, so n squared is equal to sine squared phi naught by 2. 1 minus n squared sine squared theta That allows us to complete the transformation, and this here, as we can see, is a complete elliptical integral of the first kind, thus allowing us to describe our system in terms of the amplitude of oscillations.